In this presentation, I will talk about the earliest properties in terms of shrinkage for 3D printed elements, how we can measure them, what inference we can make out of the measurements that we make in 3D printed elements, like how we can analyze these things. It's mostly gonna be in terms of like how we can understand what we are observing rather than actually say like effects of different quantities or different materials in the print. So to start with, I'll talk about like the problem statement, why shrinkage is studying shrinkage is important. Then I'll give you some background information of like how we are measuring shrinkage, how we are validating that the way we are measuring shrinkage is most probably correct, and how actually the numbers that we get in shrinkage measurement in 3D printed wall systems and how they can be understood in terms of like why we are getting such numbers. And I'll talk to you in a short conclusion about the things. So again, similar thing, 3D printing, concrete, you can print without formwork, architectural freedom. Again, in terms of shrinkage, the biggest important part is like there's no formwork, so it's exposed. Like the high surface exposed area is the biggest problem, causing your moisture to be lost from the printed system and causing it to shrink and crack. So in terms of printing, because there's high surface area and the other thing being the high binder content. So basically it gives you a plastic shrinkage as well as autogeneous shrinkage because of the concrete area and absence of formwork, as I told before, like causing a high surface area exposure, relating it to more significant moisture loss in the initial concrete mix. So because of that, if you do not cure it properly, or if you even sometimes if you try to cure it properly, there you'll see like there will be cracks forming on your printed elements. Some might be like a very significant vertical cracks that might form. Some might be like smaller cracks that you see in printed elements. Now, there are like different problems with it. It might be aesthetic problem in the sense of, okay, you don't want to see a printed element cracking like that. Second, in terms of durability, you will see like more chloride ingress, moisture ingress in these printed elements because of the crack. The other being like the final mechanical properties. Because there's already a crack, there's a stress concentration point. Now, if you put it in compression or flexure, it's just gonna give you lower strength than you expect. So design-wise, shrinkage is important. Again, based on like how much surface area you do expose, cracking chances can go higher. So again, in typical application case for industrial purpose, maybe the binder contents are slightly lower, but in our case, when you do in a lab, we usually have like higher binder content, resulting in a more autogeneous shrinkage too. So there are like different measurement techniques to actually see displacement fields and actually capture the strengths in the printed elements. Of those, there are like some contact methods, some non-contact method, of which, for some reason, it's directly. Yeah, so we are using the digital image correlation. Basically, we are using two point gray cameras placed at a distance, focused on the printed element. I'll show you slide details on how we actually prepare the sample for it. But to do it, first we have to kind of validate that you can use DIC on a concrete system to actually capture these microstrengths. So for that, we are like using different mixes. I'm showing it in terms of 4 mixes, but again, I'm not gonna go into specify like why one shrinks more and the other shrinks less in this presentation, but I'm gonna show that we validated it over like different mixes, because you can't just validate for a single mix when you are doing a new technique, right? So for these systems, we initially selected few of the binder systems that are printable. Again, the mixes that you see here are such that they are extrudable and they are buildable to a certain height. When I say buildable, it's not like it will collapse at 1 meter or so. They have like low buildability because we wanted to make it more fluidy. We have like higher, lesser buildability in these mixes that we designed for the shrinkage. But we actually do the cast specimen first to validate DIC, then we do the printed specimen to see what the printed effect is. So in terms of cast specimen, we do 2 kind of measurement. One, the typical conventional method of measuring through the measurement extensometer measurement, and the other one is through measurement with DIC. So in DIC, what we usually we have done is once you cast the samples, we are using the same samples for extensometer and then a separate same batch, separate beams for DIC. So we speckle the beams right away. You can see like we can do multiple beams in a single frame. So we did like 4 different beams in the single frame, and we speckle them white and a black pattern on the top. This black pattern is required for the measurement of displacement, in the sense of the camera takes picture of the sample each second, and it will give you based on the dots movement with pixels being there. Like again, we use VIC 3D in the terms of correlated solution software to do analysis. We are not using anything external. We are using the software provided by them. So camera, everything system by them. So it basically gives you a subset size and it measures your movement. So the bold lines here are the measurement in terms of actual extensometer, and the dotted points are basically based on DIC measurement for each day. Again, DIC measurement we took each frame for a minute. We can do it in terms of like longer period in terms of hours and stuff also, but we did it in terms of 1 minute, and we have like a lot of data of which we are filtering out and showing lesser points, but we do have like a bunch of points. But if I plot it here, it will just look like a messed up point collection. So we just plotted few points only, and you can see like more or less typically if you see like the darker shade of each color is more towards the extensometer reading and the lighter shade is towards the DIC reading. They are quite close by. Some results are like typically for a longer period of time, some are lesser because again based on DIC availability we kind of did not do a few to the long period of time, but at least as a correlation we can see like despite the paint being there and everything being there, there's not much difference on the DIC that we are calibrating through the shrinkage measurement through the DIC. It has been shown elsewhere also. The paint that we are using is acrylic paint and it does not have as much effect on the moisture diffusion in the system, so there's not much difference within the system. It's not 1-to-1, but it's close by, so we are not using any correction for the values as of it is. So now how do we correlate it into printing? In a cast system you just have the cast sample, it's free to move, but in printing what we have to understand is like there's a restraint. Be this your print bed, the first filament you print is restrained by your print bed. Unless you are moving it from the place, it's just gonna stay strained in the sense of it's not a free shrinkage. So now if you put the second layer, because the first layer is restrained by the print bed, second layer is restrained by the first filament. Similarly, it keeps going up, and like the topmost portion is free to shrink, but technically as you go bottom, it's not as free. And similarly, if you put second filament on the side, there's a horizontal restraint on the shrinkage too. I'll show you why this is very important to understand in the terms of like reading that we get. But there are like two different kind of restraint. One is the restraint against height, and the one is the restraint against the thickness. Basically, the more you print, the more height you print, the restraint will kind of be different in terms of each filament or each jet value that you have. So that being your typical restraint effect, what we ended up doing is like we printed 4 filaments. Like again, you could do more, less, you can do higher. There it will be slight different in terms of analysis when you do actually analyze those results. But with the 4 filaments, we are doing it because we want to keep it at a certain distance, and this is like we want to make utilize of near enough and better enough images to do the DIC analysis. So once we have the 4 filaments, we basically consistently did 4 filaments in the terms of like if you see it might not be as clear, but they are speckled in terms of two pattern. Initially we start with a white speckle. Like I showed you before in the cast sample, because it's already dried off, we usually put a very thick coating of white paint and a black speckle over it. But in terms of fresh print, they are already kind of blackish in the terms of the mixes because of the water content. So we only do white speckle initially, because we do not want to restrict the moisture movement even if there is some. So once a certain hours, like 2-3 hours has gone past, we again put a complete white background with the black speckles so that we can do long-term shrinkage readings too. So in terms of DIC, again, if you see few portions in the middle that are not showing up the green part, it's basically around the interlayers where it's not perfectly flat surface on the front. So that's why like there are few surfaces where the speckle will not be that particularly good, because again the speckle is on a floor, and we have to make sure that it's not like messed up, because it's one try you get with the printed samples once you print it. So it's quite hard to speckle this, but again you can see like the profile is quite good enough to kind of capture most of the areas that we have in the printed wall system. So with this, we did again single filament. When I say single filament, it's 4 layers with one single width thickness. The filament thickness, for the sake of completion, the filament thickness are 30 mm height and 30 mm wide. So each filament, we did one single filament for the 3 mixes that I showed you before, and we did double filament. So when I say double filament, it's basically 2 filaments side by side and 4 layers on top of each other. You can see like there are numbers all over the place, in the sense of like you can see the first filament that you see in each print shows the least shrinkage, while 4th filament is the highest shrinkage. And if you see, the one single filament layer shows higher shrinkage, while the 2 double filament shows lower shrinkage readings. It's surface shrinkage that we are reading through DIC, but why is the difference in there? Here comes the use of the restraint effect, like the restraint that I talked to you in terms of height and the filament thickness, that comes up here. That restraint is showing a different number instead of a free shrinkage reading. So this we are calling as observed shrinkage. So how can we know that the observed shrinkage is correct? What is the rationale between saying that, okay, whatever shrinkage I am reading is correct? So there's a restraint effect that we have to remove to actually get a free shrinkage value. So for the height restraint, we basically define a coefficient based on the axial deformation. So this is basically a ratio of axial deformation at a certain height, like basically a vertical deformation at a certain height with respect to the total deformation the element goes through. And that is your restraint at a certain height. So at top, being the 120 mm, because it's 30 times 4, 120 mm, the restraint is going to be 0. And at the bottom, where it's the surface with the print base, the restraint is 1. So once you have this, you can use the E1 equation to typically remove the restraint effect from height. Now we see like for different mixes, when we do remove the restraint effect from height, the values are similar. So in that, it's basically because of the higher restraint on filament 1 that we are seeing lower shrinkage readings, while in filament 4 we are seeing higher shrinkage reading, because free shrinkage is always higher than the restraint shrinkage, right? So would it similarly correlate in the double filament? Yes. So in double filament also, we see that if we remove the restraint effect, we see similar values, at least for the 4 layers. But now you can see like this, for the single layer and the double layer, the values are different. If you see on the left-hand side, the typical value that it calibrates up to is about 1 microstrand, while in the lower one, it's like 0.6. So it's like 60% of it. Now, how does that happen? Like, why is there a less shrinkage on a double filament sample? So it's a more of a volume based, in the sense of like the amount of surface area you have exposed in terms of the print versus the actual volume you print. Now printing double filament basically adds up a smaller area on the top, because now it's basically the 2 filaments are attached on one side. So that area translates to the other side, and the top surface area in a very smaller sense increases. So there's not typically a much surface area increase, but there's a twice the volume of increase. So there needs to be a restraint effect in terms of thickness that we have to know. So this again, like, it's not based on a certain equation, but it's mostly based on a continuous trial and error on different mixes that we did for different layer heights. The restraint effect on direction of thickness follows a power law. So power law in terms of like, if you see it in terms of this value, it's like 0.6 times the 6 to 6.3 times the previous filament if you go twice the filament each time. So when this restraint effect is calculated, we've validated it for 4 filaments also, but I'm not showing that here. But when you actually remove that restraint effect from the double filament, now your value from the double filament and the single filament are similar. Now, I am calling this a free shrinkage, but again, I am in the previous slide, if I did not point it out, but if you remember, I assume the restraint against thickness for the single filament to be 0. So when I am saying E free is this, the free shrinkage is this, it's based on a single filament. I am calling the single filament's restraint after removing the vertical restraint as E free. Again, if you actually do a free filament print, it most probably will translate to be a slightly higher numbers than this. But again, we are able to kind of remove the restraint effect and see that, okay, these are typical restraints that you see in the printed element. So in terms of strain field displacement, again, we saw that we can use DIC to capture the displacement field in fresh printed concrete. Like these were printed concretes, the measurement were taken after 15 minutes from printing to up to 24 hours, 48 hours after printing. So these are like the plastic shrinkages that usually are the most detrimental in printing. So we can capture that in terms of DIC imaging. We can actually see, understand why with different layer heights, with different print heights, different print thickness, why the strengths are different. And we can have like a rationale between like, okay, what happens if you print a double wide filament wall? What happens if you print a 4 filament walls side by side? Again, shrinkage will decrease obviously for your total, but again, it might translate in terms of, because there's higher restraint, you could end up having cracks, because now your restraint, the material actually wants to shrink whatever it wants to shrink. You are restraining the shrinkage. You are not removing the shrinkage at this point of time. So it might crack. There might be problems because of those reasons. But again, this is a general idea on like how you can understand the typical shrinkage behavior in a printed samples. Again, we are working on to find like actual values to show the free shrinkage of these printed elements to print bits. The problem being like we are facing few issues in the terms of like it, if you print a single filament, it starts cracking right away because of the environmental exposure condition. Everything is like in a lab environment with 25 degrees Celsius and about 45% relative humidity. So on that, like we are working further in terms of defining shrinkage properly in terms of mix, water content. We are trying to come up with more detailed explanation on this. I think with that, I'm done. Thank you.
Thank you very much.